Next, most important, reactions of metal alkenes. Reactions of metal alkenes. Please listen. You know, normally an alkene, for example, this is an alkene, CH2, CH2, double bond CH2. Okay, on reaction with a nucleophile, Nu minus, nucleophile having negative charge, alkene pi electron density, alkene having very high pi electron density, so alkene is also negatively charged. So both of these will not react. There is no reaction. Alkene generally not react with the nucleophile. Why? Because alkene is also an electron rich center. Nucleophile is also electron rich. So two electron rich centers will not react. But at the same time, a metal alkene, a metal coordinated to an alkene, CH2, double bond CH2. Okay. As a result of the coordination of alkene to this metal, a slight positive charge developed at these two centers. Why? Because the electron density is donated to the metal. The alkene electron density is donated to the metal, so a slight positive charge developed at each carbon. So this on react with a nucleophile. It will react with a nucleophile. Attack may be at either of these two centers. So metal alkene generally react with reaction with nucleophile Nu minus. That is the important reaction of metal alkenes. Okay, so please listen. Here an important rule is there. After studying that rule, then only we can work out question. Rule is DGM rule. DGM rule. DGM rule is Davis-Green-Mingus rule. Davis-Green-Mingus rule. Based on this rule, we can work out the questions of reaction with the nucleophile. A metal alkene react with the nucleophile. First point, 2 points are there. First point, open alkene react faster than closed alkene. That is the first point. Open alkene react faster than closed alkene, or open alkene is more reactive. For example, double bond, single bond, double bond, single bond, and a 6-membered benzene. What is the difference between these two? Both of them having 6 carbon, here also 6 carbon, 3 pi bond, but one is open, other is cyclic. So definitely comparing these two alkene, open alkene is more reactive than closed alkene. That is the first Davis-Green-Mingus rule. So in your complex, 2 alkenes are there. You are reacting with a nucleophile. Nucleophile will attack which alkene? Definitely open alkene. So open alkene is more reactive. Once again, an organometallic complex is there. That organometallic complex containing 2 alkenes there. Okay, you are reacting with a nucleophile. One alkene is open, other is cyclic. Definitely attack will be at open alkene. Open alkene is more reactive. Okay. Then second point, even center alkene more reactive than odd center alkene. Even center alkene more reactive than odd center alkene. For example, 1,3-butadiene, both 1,3-butadiene and cyclopropyl anion. Cyclopropyl anion. Okay. Cyclopropyl anion. Which one is more reactive? This is even center. 1, 2, 3, 4 carbons are there. Here only 1, 2, 3 carbon. Definitely even center is more reactive than closed. So in general, open more reactive than closed. These two are open. These two are open. In the case of open, even center alkene is more reactive than odd center alkene. Okay. So based on these two rules, a series is given in some textbook. You can follow that series, then you can easily practice the question. Okay, so reactivity series, reactivity first of all you have to think that open more reactive than closed, then odd, sorry, even more reactive than closed, even more reactive than odd. The most reactive alkene is ethylene, CH2 double bond CH2. Then 1,3-butadiene. 1,3-butadiene is the second one. Then 1,3,5-hexatriene. 1,3,5-hexatriene. Then closed 6-membered cyclobutadiene. Okay, so ethylene, ethene is the more reactive, then cyclobutadiene, then 1,3,5-butadiene, 1,3,5-hexatriene. All these are open. All these are open system. Then it's a closed analog. It's a closed analog is 6-membered benzene. It's a closed analog is butadiene. All these are even centers also. Then greater than cyclopropyl anion. Then its reactivity greater than 1, 2, 3, 4, 5-membered carbon. Negative charge delocalized. Greater than Cp, cyclopentadienyl anion. Greater than, last one, tropylium anion. Tropylium, not anion, it's a cation. The negative charge is delocalized over tropylium cation. Okay, so that will be the reactivity order. So in the same complex, an ethylene and 1,3-butadiene is there. Which alkene is more reactive? Definitely ethylene is more reactive. 1,3-butadiene and 1,3,5-hexatriene is there. This will be more reactive. When an open and closed is there, open will be more reactive. When an even center and odd center is there, even center is more reactive. So please follow this order. Okay, then moving to some questions. Please copy the series. So our first question, Fe coordinated to an alkene. Here a carbon monoxide is there, and it is connected to SCP. Okay, overall charge plus on reaction with a nucleophile MEO minus. So it's a metallalkene compound. This is also alkene. Cp is, what is the structure of Cp? This is the structure of Cp. Minus. Okay, cyclopentadienyl anion is called Cp. Okay, so both are metallalkene complexes. metallalkene complexes. Okay, so on reaction with a nucleophile, my question, nucleophile will attack at which center? At this alkene or this CP? Okay, you know the series, most reactive is ethylene. Whenever ethylene is there, definitely nucleophile will attack at any of the center of ethylene. Both are identical. In the case of ethylene, both ends are identical. So OMe minus will attack here. This pi bond shift towards this corner and that will connect to metal. Okay, when OMe minus attack here, this pi bond shifted to this corner, CH2 minus. That CH2 minus will coordinate to the metal. Then how you can write the product? Fe Cp as such, Cp is not reacted. Here a carbon monoxide is there. Here a carbon monoxide is there. OMe minus attack this carbon, then this carbon is connected to metal. For example, this is carbon A, carbon B. When OMe minus attack at the carbon B, A will connect it to iron. This is carbon A, carbon B, this carbon containing OMe. This is carbon A and B, carbon B containing OMe. So that will be your product. Once again, two alkene systems are there. That on reaction with a nucleophile will attack any of the centers of this alkene. Automatically this pi electron density will shift towards the metal. Then metal connected to this carbon OMe. So that will be your product. This type of questions are favorite for any competitive related exam. Reactivity order based on DGM rule. Davis Green-Mingus rule. Okay. Then write the next question. Question number 2. Fe and here a 6-membered ring is there. Here a 6-membered ring. Here also a 6-membered ring. Okay. Overall charge is equal to 2 plus. On reaction with MeO minus. Both are alkene system. Both are metallalkenes. So benzene. This is benzene. Benzene containing 3 double bond. Okay. So an important point. Number of attack equal to number of positive charge on the complex. Number of attack is equal to number of positive charge on the complex. Here complex having 2 positive charges. So OMe minus will attack 2 times. Here complex having only 1 positive charge. So OMe minus will attack only 1 times. If complex is neutral, there will be no reaction. Okay, so a nucleophile will attack. If neutral complex, no reaction. 1 positive charge, nucleophile will attack 1 time. Here 2 positive charges there, so OMe attack 2 times. In the first case, OMe minus will attack at one of the carbon. All are equivalent. At one of the carbon. Then you get Fe. This ring as such, 6-membered. Okay, here at one of the carbon an OMe is attacked. Then the pi electron density delocalized over only 5 carbon except this carbon. Okay, so this eta 6, this is eta 6, this is also eta 6, this is eta 6, this is eta 5. Okay. Then charge equal to 1 plus become 2 plus become 1 plus. Find the electron count. This is iron 8 plus 6 14 plus 6 20 minus 2 18. Here 8 plus 6 14 plus 5 19 minus 1 equal to 18. All are according to 18 electron rule. But still 1 positive charge is remaining. So what happens? Again an OMe attack. OMe minus again attack. Then my question, Then my question, here two alkenes are there. In which alkene the OMe minus attack? In which alkene the OMe minus attack? Both are cyclic. Both are cyclic. But here it is an even center. Pi electron density delocalized over 1, 2, 3, 4, 5, 6 carbon. It is an even center. Here pi electron density delocalized over 1, 2, 3, 4, 5. Only 5 center. So it's an odd center alkene. It's an even center alkene. Definitely OMe minus will attack even center. Even center. So what will be the final product? Here iron is there. Okay. It is coordinated to okay, here an OMe, here also an OMe. More favorably, it will be trans to each other. Then maximum stability, OMe. Here pi electron density delocalized over 5 carbon. Here also pi electron density delocalized over 5 carbon. So that will be your final product. Okay, so metal alkenes react with nucleophile. Number of attack is equal to number of positive charge. Then write the next question, my dear students. Third question. MO, molybdenum, cyclopropyl anion, 1,3-butadiene and benzene. Okay, overall charge is equal to plus on reaction with any nucleophile Nu minus. 3 alkene systems are there. Nucleophile will attack on which alkene? Davies Green-Mingus rule, DGM rule. It's odd center, it's even center. These two are even center, 6, 4, 3. Odd center less reactive than even center. So this is cancelled. So comparing these two, 6, 4, both are even. But this is cyclic, this is open. Definitely open will be more reactive. Okay. So nucleophile will definitely attack. Since it is an even center, it can attack at any of this position. Normally terminal position is preferred. So attack will be at the terminal carbon. Nucleophile will attack terminal carbon. Then this pi electron density shifted towards here. Then it is delocalized over 3 carbon. Okay. Here a double bond is there. Nucleophile attack at this double bond. Then that double bond will shift towards this corner. Then 1, 2, 3 delocalization over only 3 carbon. This is molybdenum. A 6-membered benzene is there. Here an allyl is there. Okay, it is connected to CH2 nucleophile. Clear? CH2 nucleophile. That will be your product. I think you didn't get the concept. This is butadiene. This is butadiene. When this nucleophile will attack at this carbon, this pi bond shift towards this corner. Then you will get here a pi bond is there, here a negative charge, here the nucleophile attack. Now the resonance only between these 3 carbons, 1, 2, 3. Resonance is between these 2 carbons. This is equivalent to 3 carbon resonance, a CH2 nucleophile. Okay, 3 carbon resonance, a CH2 nucleophile. That is I am represented there. Once again, 1,3-butadiene nucleophile attack this carbon, pi bond shifted towards here. So negative pi bond nucleophile. Then this will undergo resonance over 3 carbon. That is a representation. Okay, so that will be your final product. Any further reaction? No. Only positive, only one positive charge. Only one positive charge. Okay, next question. Write the next question. Molybdenum, PR2, PR2. Here SCP. Here also SCP. Okay. Overall charge equal to 2 plus. Overall charge 2 plus means definitely attack takes place 2 times on reaction with the MEO minus and also given 2 equivalent. Okay, what happens? Here 2 alkenes are there, both are cyclic as well as odd. So any of this OMe minus attack any of this carbon. So what you get? Molybdenum, PR2. Okay, here a CP as such, this CP as such. Here an OMe attack at this carbon. So delocalization except that carbon. Deloc 1, 2, 3, 4. 4 carbon delocalization. Then overall charge become 1 plus. But reaction not stopped at one more attack because one positive charge is still remaining. So one more attack, OMe minus. One more attack. My question, attack will be at which center? It's a 5 carbon center, odd center alkene. Here 1, 2, 3, 4 delocalization in 1, 2, 3, 4. It's a 4 center alkene. It's a 5 center alkene. Definitely even will be more reactive than odd. So second OMe minus will also attack on this carbon. Okay, so what will be your product? Molybdenum, PR2. Here is CP. Okay, here also a CP is there. Here an OMe. Here also another OMe. Then pi electron density delocalized over 3 carbon. What is the electron count? This is molybdenum. 6 plus 4, 10, 15 plus 3, 18. This is eta 3. This is eta 4. This is eta 5 CP. It's eta 4 and it's eta 3. Okay, so that is the question. Then next question. Then write the next one. Okay, write the next question. Molybdenum. This is CP, CO and NO. CO and NO. An allyl system on reaction with OMe minus complex having overall charge positive. Then next question, one more for a comparison. Write the next question. W. Here CP. Here also CP. Allyl system. Overall charge plus on reaction with any nucleophile, for example hydride ion H minus. So let's have a comparison. Here one important factor is there. Here which one is more reactive? Both are odd center, but CP and cyclopropyl anion, which one is more reactive? This is more reactive. Here also comparing CP and this one, this is more reactive. It is an odd center alkene, odd center. Okay. So attack will be at terminal position. These two terminal positions are equivalent, or at this middle center. Both are possible. Here also attack at these two terminal centers or this middle center is possible. These two centers are equivalent or at a middle center. So in the case of allyl system, write a note. In the case of allyl systems, in the case of allyl system, if pi acceptor ligands like carbon monoxide, nitrosyl are present, pi acceptor ligands like carbon monoxide, nitrosyl etc. are present, then attack will be terminal attack. Attack will be terminal attack. Okay, first point, if non-pi acceptor, then middle carbon attack. This is in the case of which system? Allyl system. So copy this note and give a star mark. In the case of allyl system, if the metal containing pi acceptor ligands like carbon monoxide, NO etc., then attack will be at the terminal. If non-pi acceptor ligand, then middle carbon attack. Here please listen. Molybdenum containing CO and NO both are pi acceptor ligands. In such cases, which attack will be preferred? Terminal attack. OMe minus will attack any of these two terminal carbon. Then pi bond shift towards this. Here a pi bond is there. You can represent this as allyl anion is represented as, allyl anion can be represented as a double bond and, allyl anion can be represented as a double bond and a negative charge. That is represented by a delocalization. Okay. So when this attack here, this pi bond shifted towards this corner, your final product can be represented as molybdenum. Here a CP, here a carbon monoxide, here a NO, negative. That two negative will coordinate here, and here an O. One carbon is also there. CH2, and here a carbon with OMe. So that will be your final product. Okay, absolutely, that will be your final product. Clear? Here a negative, both negative will make a double bond and coordinated like this. So that will be your final product. But here CP and CP is not at all a pi acceptor ligand. Okay, CP is not at all, it's a pi star ligand having very high energy. So CP is not at all a pi acceptor ligand. So in the case of non-pi acceptor ligand, middle carbon attack. So your nucleophile, OMe or H- or whatever may be, that will attack the middle carbon. And the product can be represented as WCP, then a cyclopropyl system, hydrogen, the nucleophile attack at this carbon, and this will be your product. Here a negative charge, that will be coordinated to the metal. That's a representation of the product. So that's all about the nucleophilic attack reactions of metallalkene. Reactions will be based on Davies-Green-Mingus rule. Then formation constant based questions. Formation constant based questions. Please write a question. Based on question we can explain. For example, this is PT, here PPH3, here also PPH3, and this is coordinated to an alkene OAC on reaction with another alkene C double bond O, okay. This reaction is a reversible reaction, and this PT, PPH3 and alkene on reaction with another alkene. This alkene is replaced by the newly formed alkene PT, PPH3, PPH3, alkene, double bond O, double bond O. Okay. So, what is the oxidation state of platinum here? 0. Oxidation state of platinum is 0. Here the formation constant or equilibrium constant, K equilibrium constant or formation constant is equal to concentration of product divided by concentration of reactant. That is called equilibrium constant or formation constant, K equilibrium or K formation constant. My question, whether the reactant or product, which one is more stable? Which one is more stable? What's the reaction taking place here? One alkene replaced by another alkene. So my question, metal coordinated to this alkene or metal coordinated to this alkene, which is more stable? Which is more stable? Okay. That can be based on, please listen, in the case of product, C double bond O is an electron withdrawing group. This is an electron withdrawing group. This is also an electron withdrawing group. Electron withdrawing group means this carbon having partial positive charge. So definitely there will be back donation from metal to carbon. Metal to carbon, back donation from metal to carbon. Why? Because your platinum is in the zero oxidation state. So definitely good back donation is present. Good back donation is present because metal is electron rich. Okay. So here alkene surrounded by two withdrawing group, alkene having positive electron density. So definitely metal also electron rich, good back donation. Compared to this one, here back donation high, back donation high means metal carbon bond order or metal carbon bond strong. Metal carbon bond strong. So platinum alkene bond strong means this is a highly stable complex. This is a highly stable complex. Clear? So comparing the reactant in your product, very high amount of back donation is there. Due to back donation, platinum carbon bond order or bond become more strong. Metal carbon bond strong means that complex is a highly stable complex that will not dissociate. Here in the presence of this ligand, this is dissociated to form this product. But here dissociation does not take place. Metal carbon bond is a strong bond. So product is stable. So my question, this is an equilibrium reaction. It's a reversible reaction. Whether the concentration of product or reactant high, which one will be higher? Stable. Which one is more stable? Product more stable. Stability. In this example, stability of product greater than reactant. Stability of product greater than reactant. So, concentration of product will be very high. That means your formation constant or equilibrium constant greater than 1. That is your question. An example like this will be given, whether K equilibrium greater than 1 or less than 1, such type of question. Definitely equilibrium constant is greater than 1 when concentration of product is higher. Concentration of product higher means numerator high. So definitely K equilibrium greater than 1. So a very important question. Okay. So in such types of formation constant based question, you have to compare the stability of the reactant and product. If product is stable, K equilibrium greater than 1 because product concentration will be higher. If reactant will be more stable, then K equilibrium less than 1. Then write the next question. Please write the next question. For example, platinum. Okay. Here NR, here methyl, and here an alkene is coordinated. On reaction with and the overall charge is equal to plus. On reaction with another alkene, double bond O, double bond O. Okay, your product will be platinum N Me. This alkene is replaced by this one. Similar to the previous question, and the overall charge is equal to +1. My question, whether K equilibrium, it's a reversible reaction, whether the K equilibrium greater than 1 or less than 1, that is my question. Equilibrium constant greater than 1 or less than 1. Similar to the previous question, an ethylene replaced by this one. Okay, so here, what is the oxidation state of metal? Here 1 plus is there, this is minus, 1 minus is there, 1 minus is there, here only 1 plus, so definitely platinum 2 plus. One of the positive charge cancelled by methyl minus, Me minus. Okay, so here also platinum 2 plus. So you know, in the case of platinum 2 plus, metal electron deficient. Metal is not electron rich. Metal is electron deficient. Then there will be no back bonding like in the previous cases. There is no back bonding, or poor back donation is present, but there is no effective back bonding because your metal is electron deficient. In the case of electron deficient metal, the more stable complex is formed when a more electron rich alkene coordinate to the metal. In both the cases, your platinum is platinum 2 plus, which means higher oxidation state, so your metal is electron deficient. Metal electron deficient means there is no back bonding. So in the previous example, due to back bonding, metal carbon bond strong, product stable, but that case is not arised here because here platinum oxidation state 2 plus, platinum oxidation 2 plus means there is no back bonding. In such cases, you have to account the stability based on more stable when an electron rich alkene coordinate to the metal. So this is ethylene, and here ethylene connected to 2 electron withdrawing group. So definitely this alkene is more electron rich. More electron rich alkene coordinated to the electron deficient metal. More electron rich alkene coordinated to the electron deficient metal. So your product is stable. Reactant is stable means K equilibrium less than 1. So an important case, because why K equilibrium less than 1? Reactant more stable than product. Clear? So this type of questions very important. H1 NMR spectra of metal alkenes. H1 NMR spectra of metal alkene. Write a question, find the number of signals, H1 NMR signals. Find the number of signals at low temperature and high temperature of the following complex. Find the number of H1 NMR signals at a low temperature. You have to find at a low temperature and the high temperature of the following complex. Okay, so here complex is PT Cl3 which is coordinated to an alkene CH2 double bond CH2. We are discussing about H1 NMR spectra. H1 NMR spectra. Here 4 hydrogens are there. 1, 2, 3, 4. If these 4 hydrogens are in 4 environment, 4 different environment, then it will give a 4 signal. If all the 4 hydrogens are in 4 different environment, it will give a 4 signal. If all the 4 hydrogens are in same environment, all the 4 hydrogens give 1 signal. That is the basic principle of NMR. Okay, once again repeating, in this complex 4 protons are there. In H1 NMR spectra only protons give a signal. In H1 NMR spectra only protons give a signal. Here 4 protons are there. Suppose the 4 protons are in 4 different environment, it will give a 4 signal. Suppose all the 4 hydrogens are in same chemical environment, all the 4 give only 1 signal. Okay, so in H1 NMR, if protons are in same chemical environment, they will give same signal. If protons are in same chemical environment, they will give a same signal. For example, this is platinum, it's having square planar geometry. This is chlorine, this is chlorine, and you know the alkene is perpendicular to this plane. Alkene is actually perpendicular to this plane, but in our board it can be represented only like this. Okay, only like this. So please listen. What is the arrangement of this alkene? Suppose this is the square plane, platinum here, 1 chlorine here, 1 chlorine here, 1 chlorine here. This alkene is perpendicular, double bond perpendicular, 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, 1 hydrogen here. Then my question, what is the environment of this hydrogen? At the top 2 hydrogens are there. It's an environment, here a chlorine, here a chlorine. At the top 2 hydrogens are there. The environment of both the hydrogens are 2 chlorine. For example, the environment of this hydrogen and this hydrogen, it's at the top, that is this chlorine and this chlorine. So both the hydrogens are in same environment. Similarly, 2 hydrogens below, its environment is this chlorine and this chlorine. So below 2 hydrogens are there, their environment is also, the environment of these 2 hydrogens is also 2 chlorine. Same. So all the 4 hydrogens are in same chemical environment. Once again I am repeating, this is platinum. Here a chlorine. Alkene is perpendicular. At the perpendicular position 2 hydrogens are at the top, 2 hydrogens are at the bottom. What is the environment of these 2 hydrogen? Environment is here a chlorine, same environment. Environment of bottom hydrogen, here a chlorine. So environment of all the hydrogens are same. So at low temperature, it will give only 1 signal because all hydrogens are in same chemical environment. Then at high temperature, only 1 difference. This platinum alkene sigma bond undergo rapid rotation. Due to that rapid rotation, all environment equivalent. If rapidly rotating, environment does not change. So then also all the 4 hydrogens give 1 signal. So this is the answer. At low temperature 1 signal, at high temperature also 1 signal, because the environment of all the hydrogens are same. Okay, then write the next question. Please write the next question. Find the number of signal. Find the number of signal for the complex. Number of signal for the complex. This is the complex PT. Here chlorine. Here another chlorine. Here bromine. Okay. Here an alkene. And this alkene having 2 hydrogens. Find the number of signals at low temperature and high temperature. Same. What is the difference? Here one chlorine is replaced by one bromine. One chlorine is replaced by one bromine. Okay. This is a bromine. That is the only difference. Same. Imagine. Find the environment. This is the square plane. Platinum at the center. Chlorine. Here alkene is perpendicular. 2 hydrogens above, 2 hydrogens below. If 2 hydrogens above, what is the environment? These are the 2 hydrogens above. For first hydrogen, its environment is chlorine, and second hydrogen, its environment is bromine. Clear? 2 hydrogens are there. For first hydrogen, here a bromine is there. Here a chlorine is there. Here a bromine is there. Chlorine, bromine. For first hydrogen, alkene, 2 hydrogens are there. For one hydrogen, its environment is chlorine, and for other hydrogen, its environment is bromine. Similarly, these 2 hydrogens are below. For one hydrogen, its environment is bromine. For other hydrogen, its environment is chlorine. So total 4 hydrogen, but only 2 environment. 4 hydrogen, 2 environment. You can refer that environment. This hydrogen marked it as green, and this chlorine are in same environment. Think that. Then this hydrogen as a box and this bromine are in same environment. Okay. Similarly, this hydrogen and this chlorine are in same environment. This hydrogen and that bromine are in same environment. That is the method of marking. Think in a perpendicular way. Alkene is perpendicular. These 2 hydrogens are perpendicular. This hydrogen is in the environment of this chlorine. This hydrogen is in the environment of this bromine. This hydrogen is in the environment of this chlorine. This hydrogen is in the environment of this bromine. So total at low temperature, 2 signal. At high temperature, what happens? At high temperature, what happens? High temperature, there is a rapid rotation of this bond. Rapid rotation. During rapid rotation, there is no change in environment. When suppose it will rotate more than 10,000 times in 1 second. So at the high temperature, all environment is same. Due to the rotation, it does not feel any difference in the environment. So at the high temperature, all protons are in equivalent environment and only one signal. Listen. So at low temperature, 2 signal, and at the high temperature, only 1 signal. That is the H1 NMR spectra of this complex.